Welcome to Hot Chips 30. Keynote 1. Spectre and Meltdown.
Hi there. So welcome to the very first keynote session. My name is Partha Ranganathan. I'm from Google. So we have a super exciting plenary keynote session today. And as you heard in the morning, we are trying out something different this time. We have four talks that are going to go tag team, and we have a panel at the end as well. So our very first speaker is Jon Hennessy, and he's going to be talking about the broad overview of what the problem statement is and how security is very important. And Jon probably needs no introduction to this audience. He was president of Stanford from 2000 to 2016. He's currently a director of the Knight Hennessy Scholars Program at Stanford, a member of Cisco Systems, and a board member at the Moore Foundation, and he's also the chairman of the board of directors at Alphabet. He's won a bunch of awards. Most recently, he is, along with Dave Patterson, the recipient of this year's Turing Award. The second talk is from Paul Turner from Google, and Paul will be talking about the journey of how Google kind of identified the Spectre Meltdown bugs and what happened there, and he's going to be talking about that. And Paul is an engineer and tech lead in Google's technical infrastructure group, and he leads a group that drives several areas of concurrency at Google. He's been working on this pretty intensively, and I think you'll find his insights on this whole space very interesting. The third talk is from Jon Masters, and he's going to be talking about the software implications. Jon works at Red Hat, and he does a bunch of different things at Red Hat. He's the chief architect there. He's the co-author for the core specifications for ARM servers. He leads the Linaro Enterprise Group. He's also on the steering committee for the C6 software working group as well. And he has authored a lot of books on Linux technology. And then finally, we close the keynote with a talk from Mark Hill. Mark Hill is from academia. He's a professor of computer science at the University of Wisconsin-Madison. And he's been researching parallel computer system design and memory system design for a long time. And he's a fellow of both the IEEE and the ACM as well. And then we will conclude with a panel. In terms of the logistics for this presentation, we're going to go through all the four talks, so please hold your questions till the end, and then we will have what should hopefully be a pretty engaging panel discussion at the end as well. So with that, please join me in welcoming our first keynote speaker, Jon Hennessy.
Thanks, Partha. So the world has changed a lot. And it's changed a lot for a number of important reasons. First of all, security is more important than ever. I am a product of, I went to school in the 1970s. That was an era when we believed software and formal mechanisms and verification would close all holes in the world and we wouldn't have to worry about security. Well, that didn't exactly work. In fact, somebody was telling me about a case where one company proved that their architecture was secure. The problem was there was a bug in the proof. So we've changed a lot. Lots more personal information is online. Like thousands of other people that have worked in advisory capacity for the US government, the US government gave away my social security number, the social security numbers of all my kids, my family, their address, all the information you need to go open a credit card account. Thank you, US government. But it shows how critical the issue has become. The cloud world has made this even more important. You're sharing the same piece of hardware with other people. You may be even sharing it with somebody who regards himself as an adversary. State actors and organized cyber criminals have become much more aggressive. There are some people in this audience that are old enough to remember when hacker was considered a compliment as opposed to somebody who was breaking the law. But the game really changed about 20 years ago, where basically organized groups would exploit holes for financial and other reasons. And that's a big change in how much we need to worry about security. Finally, the complexity of modern systems, so many web services, has meant that the surface area that you can attack has gotten much, much bigger. And it's much easier for people to find holes. That growth in complexity has simply outstripped our security mechanisms. But there is a change here. Most attacks are traditionally software-focused, buffer overflow being the classic example, and they still are the majority of attacks. But as we'll see, things have really changed with Spectre and Meltdown. Spectre and Meltdown both exploit what we call side-channel attacks. Side-channel attacks are not new. They're an old idea. I remember the first side-channel attack I saw in the 1970s exploited a hole in how TOPS 20, the DEC operating system, checked passwords. It would check a password one letter at a time, and basically as soon as it found a mismatch, throw back. So what you would do is take the password and place it on a page boundary and notice whether or not you got a negative result before or after the page boundary the page fault occurred. And by timing the page fault, you could figure out whether or not you had guessed the next letter of the password correctly. And you could break through the password that way. So it's a side channel attack, meaning you look at performance or some other metric to understand whether or not, what data is being extracted from a security viewpoint. What's really new with Spectre and Meltdown is that most of these holes have traditionally been software holes. In Spectre and Meltdown, it is a hardware flaw. The architects are the people that did it in some sense, although we'll see when we hear Mark Hill's talk, there is a lot of subtlety about what is right and wrong in terms of this. Meltdown and Spectre, there are now multiple versions of them, and there's a lot of suspicion that they're just the first of many variants of this form that exploit the holes created primarily by speculation. Just new ones came out just last week at Usenix, L1TF and Foreshadow. They break the virtual machine barrier, actually. And in the case of Foreshadow, you can actually extract information from an SGS enclave. So the SGS enclave that Intel implements is designed to protect the most important things, like encryption keys. You can actually break through that SGX enclave with the Foresight hack. Okay, so finally, it's painful or nearly impossible to fix all these problems just in software. Painful meaning you've got to recompile software, you get a performance hit, and you cannot close them all. So you're really mitigating the reducing the number of bugs and the rate at which information gets leaked. So, leveraging speculation in a side-channel attack. How does this work? Well, remember speculation, you execute instructions early before you know they're definitely needed. You buffer the results. In fact, when we worked on the early speculative machines in the 90s, in the early 90s, the thought was, because we won't commit anything, we'll maintain precise exceptions, we'll delay any action on the ISA macro level until the instruction is known not to be speculative. We thought everything was okay. If you speculate and you guess wrong, you just roll it back. The problem is the side channel creates a hole. You can see the state, you can see the microarchitectural state change. And that's what you're observing with the side channel, the change in the microarchitecture. Not the macroarchitecture, but the microarchitecture. So how does Meltdown work? Meltdown is the easiest, I think, of the holes to understand. It's particular to Intel processors because they use a more aggressive form of speculation. So here's basically how it works. Simple. We're going to see more detail in Paul and John's talk, but this is a general setup so you understand the basics of how these things work. First, clear a section of the cache. That's just so you can get nice measurements back from it. Then prime a branch predictor for a branch B so that the branch is predicted not taken. Again, this just increases you don't have to do that, but it makes it much better if you do that. Then you have a branch. Branch if equal, R0, and skip around an instruction. Okay? So branch if R0 and R1 are equal, except this time the branch is taken. Okay? Because the branch is taken, I'm eventually going to squash the data after the instructions right after the branch that are speculative, like that load byte instruction. It will be squashed. But if you send the cache address out and fetch the data from memory, you change the cache state. Remember, the first thing we did was make sure that section of the cache is wiped out. So now you've speculatively done an instruction, you take a value, you change a cache line, and now all I have to do is go examine the cache line, see which particular cache line is now present in the cache, and I know that the corresponding value corresponds to that particular cache line. That's how the side-channel attacks work. One of the other recent breakthroughs is one called NetSpectre. So this is an amazing hole because it creates a security hole using speculation across a local area network or within the same system area network, let's say on a cloud, in a cloud. So I'm leaking data without actually running code on the same machine as I'm extracting the data from. I'm running on a remote machine. Okay, and it's based on the same idea. You have a leak gadget and a transmit gadget. The leak gadget sends valid packets to train a branch predictor. Then it sends an invalid packet, and in that shadow of that invalid packet, it extracts a piece of protected data. And then a transmit gadget is a way to get that data out. You can't observe the state directly, so you use another network request to determine what has changed in terms of the packet handling. It's a noisy channel. It takes a lot of time to get data out of this channel because they're on two separate machines across a network, but it leaks. And if you're familiar with the data about how long it takes from the time an intruder breaks into a machine till the time that intruder is discovered, you know that on average it's about 100 days. So even though it's only leaking a few bits a minute, it could leak it for 100 days. So lots of data could be leaked over time. So we've got a set of security challenges. Software flaws, obviously. Hardware has a responsibility, and computer architects have a responsibility to reduce the area available for attack and mitigate those attacks by creating security mechanisms which reduce the probability that a hole in the software system will expose lots of highly confidential information. Those mechanisms need to be both effective and efficient. In the 1970s, there was a lot of work poured into sophisticated protection mechanisms, capabilities, and all kinds of mechanisms, gates and multi-X and things, which eventually all got dropped. And they got dropped because they probably weren't the right match for what software designers thought they needed, and they were too inefficient at the time. They involved lots of indirection, multiple memory accesses per real memory access. Those are all things we know how to fix now. We have mechanisms for dealing with those kinds of things. So it's time, I think, to begin re-examining some of those more sophisticated mechanisms and see if they'll work. Finally, hardware flaws. We simply can't design hardware that has security flaws in it. That's an obligation of everybody who works on computer architecture. We can't do that. No matter how much performance could be gained, you can't open up a security hole. So we've got to go fix those problems. The fixes can be difficult, and as you'll see in Paul and Jon's talk, the fixes can sometimes negate the performance advantages that are gained by the hardware mechanism that we cleverly put in. Unfortunately, lots of us missed this problem for somewhere between 15 and 20 years. So there are lots of processors out there that have these holes in various forms. We've also got to build better mechanisms, and I think one of the things Mark Hill will talk about is how we define architecture differently to enable us to focus on these. So I think it's going to be an exciting panel, and with that introduction, we'll move on to talk to the real experts. Paul, you're up. Thank you.
Thanks, John. So hi, my name is Paul, and as John, one of my panelists, suggested, now would be a good time for questions. Now, actually, despite this being a topic on out-of-order execution, we are going to go through the slides in order, thankfully. So, a bit of background. I'm an engineer at Google, and it's been an interesting 12 months. In fact, when Partha kind of came to us with the idea of doing this talk, both John and I were kind of looking at our watches and kind of looking at last week's disclosure date and going, okay, but it's going to be a bit tight. So yeah, it's definitely been interesting. But we kind of wanted to give you some background on how we've been looking at these problems, how we've been thinking about these problems, kind of what's been going through our heads. So Google Project Zero is a team at Google that does research on kind of security 0 days. They're trying to find these fundamental holes before they can become 0 days and mitigate them. I'm not actually a part of Project Zero. I'm part of the kind of team that fixes it. In some ways, you can think of Project Zero and Jan, one of the researchers that co-discovered this, as Wreck-It Ralph. And then John and I are like Fix-It Felix. We kind of come around and keep rebuilding everything after. So early last year in 2017, Jan Horn, one of the researchers of Project Zero, co-discovered this new class of vulnerabilities. And internally, they became known as SpecHammer. So some of you may have seen this slide before. It's from another Googler, Jeff Dean. He's talked about these numbers a lot. These are kind of numbers everyone should know about a modern CPU. And actually, this slide's out of date, right? Because we know mutex lock-unlock's been recently accelerated. But it turns out that this first half of the chart is where it's really interesting. This is where processors have been trying to hide those latencies, right? It's a huge scale between an L1 cache reference to a main memory miss. So processors have been overlapping work using speculative techniques to try and hide these latencies and use predictors, speculate aggressively, increase the overlap. And when it works great, right? We can get fantastic IPC. So as you might guess, the spec in SpecHammer was for speculation. And it's kind of based on the idea that, all of the processors are doing this. And they're doing it because of that top half of that quadrant, right? If the speculation is correct, we can retire a bunch of instructions at really great IPC with no cost. And if this prediction is not correct, as kind of John was saying in his introduction, the speculation is discarded. It cannot be observed. It has no side effects. That discard is precise. Turns out that's not actually true. This was kind of the problem. This is when Pandora's box was opened. So this is kind of the new now that our journey began in. Previously, speculative execution had been thought to be data-free in its side effects. There'd been several published examples of kind of, you could reverse an AES key based on looking at things you know about the control flow of a sibling hyperthread. And you could do this because you could tell that, it took this branch, and so that gave you inference on your key space, and you could reduce the key space down to something you could brute force. But it wasn't very practical. You had to precisely know the text. You had to be able to do a pretty precise cryptanalysis. You had to be able to be forcing it to execute in that code. This was a kind of a control dependency rather than a data dependency. This new class of attacks really fundamentally broke this assumption because they showed that we could directly get data out of the speculative path. And it's worth noting that kind of Anders Fogh, this was really kind of foreshadowed in that Anders Fogh earlier last year came very close to uncovering this. He published a very good technical write-up of some experiments he did that had come within a whisker of the actual problem. And worse, these problems have existed for going on 20 years, so kind of the assumptions that we've built into our software, into our infrastructure around these properties being true are pervasive. So variant one, this is kind of where it all starts. The idea that we can speculate around some restricted part of execution, right? We have some conditional that gates access to something. Inside that something, we can touch a private memory. Perhaps we're gating on, you having the right access permission, you having the right password. And then we can touch shared memory from that restricted memory. And as John was describing, if you set up the caching on that shared memory, you can then use that to kind of infer things about the restricted memory. So variant one started as kind of caller attacking using these gadgets which export private memory into shared memory. But it's really a much more general idea than this. It boils down to, we misspeculate on some boundary. That boundary is intended to restrict execution. It might be restricting on a hardware access, it might be restricting on a software access. We'll kind of talk about both. And once you're past that boundary, it turns out that speculation can now proceed in that restricted space, even though it might not necessarily have the right to were it being retired. And this then lets you extract information from the restricted space into a shared one. So in practice, the two key examples that made variant 1 so dangerous were browsers and kernels. For browsers, we have this natural property where we've built these software virtual machines that are designed to restrict execution, right? We have this restricted context that is entirely a software construct. You have a VM that says, I cannot, I'm going to run this arbitrary code from the website, but I'm going to run it inside a virtual machine that fully gates all of its accesses. And I can ensure that it never retires anything that touches memory outside the virtual machine. That turns out to be false because those restrictions only affect the non-speculative control flow. It turns out that using these speculative attacks, you can generate not speculative execution, which runs inside this restricted space. And even better, you can use the actual memory assigned to that JIT because you've got some Turing-complete language here which has its own memory. And of course, from the VM, you can touch that memory. So you have this great space of all the secrets the VM might have, perhaps banking details, login information for another website in a browser case, and you can pass it right back using this convenient memory sidechannel that exists for hosting kind of your virtual execution. And it's notable here that the resolution really was side isolation, which was really separating these into separate execution domains, something that I'll touch on in a second. Another key example was kernels and hypervisors. Very similar problem here, where thanks to the, every operating system engineer will tell you that the growth in the virtual address space has been wonderful, right? Instead of having to mess around with addressing extensions, with windowing, we can now just direct map all of physical memory. But suddenly this has a high cost because it means that if you can generate speculative execution within this space, suddenly your restricted memory is that direct map where you can look at anything running on the system. And it also gives you this great side channel back into your own process because you can touch the cache lines that belong to you. So these two examples were really kind of why people worried so much. And also in particular for the second example, both of these took boundaries we considered as sacrosanct before this. We thought for browsers that the VM boundary between the browser and JavaScript was tight. And for virtualization, we thought the hypervisor and kind of virtual machine boundary was safe. And obviously both of these were thoroughly punctured. So I'm actually going to go slightly out of order here because variant 3 really is this generalization of variant 1. Here, the restricted space turns out to be in hardware rather than in software, right? Rather than a software protection where we say, is this within the array bound or do you have access? This is the hardware saying, do you have permission? Those permissions are the kernel supervisor bit on the page tables. And it turns out that when there's an entry in the L1 cache, that if there's the L1 cache is virtually tagged and physically indexed, meaning that you can look it up with a virtual address. And so when you can find these entries, it turns out speculation will proceed, and you can extract information from it, just like you could, right? Variant 1 is this very generic idea. We're able to get execution into a restricted space and extract data back from it. Publicly, this was what was called Meltdown. Variant 2 was a little more interesting. Variant 2 was, in many ways, the least surprising of the vulnerabilities we had, because we knew that the branch predictors had shared state, right? In particular, the indirect branch predictors. Polymorphism and kind of object-oriented code means that it's really popular to be able to call through function pointers. Obviously, the hardware has to then do a memory read to see where the branch is going to go. So what do? They hide the memory latency of that memory read. They implement a predictor. And it's worth having lots of slots for these, so what do? They don't use the full tag. They don't use the full addresses for these tags. So it turns out that yes, these branch predictions are shared between guests, between user, between kernel, and you can influence these. And this was kind of always known to some extent. Like if you'd said this to someone, they'd be like, yeah, so big deal. The problem was you could now chain this to variant 1, right? Without variant 2, we could have taken our kind of code paths that gate the kind of common execution. You could have done a huge static analysis and annotate every conditional branch that comes out of the kind of a JIT or the kernel. But suddenly with variant 2, we're faced with the fact that actually no, there's this fundamental boundary that execution can be completely hijacked at. And worse, that this boundary crosses VM contexts as well. So, okay, where are we? Where does mitigation start? Perhaps surprisingly, despite GPC actually being the ones to discover this initially, we didn't get a head start. We actually got our notification from the vendors with everyone else, which was, so this was hard. And what I'd like to talk about here is something that I think you'll find useful in thinking about what the presentations that Jon and Mark follow me. These are two ways where we've really been kind of characterizing how we think about these problems. And I think it's a useful framework for thinking about how mitigation works and how it looks like. The first is cases where how can we restore hardware boundaries where possible? And by restore, I mean cases where we really believed there was a hardware boundary, and it's just suddenly not being enforced anymore. Meltdown is kind of a very clear example of this, where there was a hardware boundary, there's the supervisor bit in the page table that we thought worked. How can we get that back? The second case is challenging. It's how can we introduce boundaries that the hardware can understand, where they did not previously exist? And if you think about something like a VM, like a JIT, where you're running code where the boundaries are purely software constructs, there's nothing today that tells the hardware what these boundaries look like. And so here we're really thinking about how can we introduce new boundaries? How can we have this shared understanding between the hardware and the executed code so that we can actually begin to protect against these cases? So mitigation against variant 3 is kind of exactly what you might expect. Here we are very much restoring these boundaries. Instead of depending on that page table bit, it turns out that we can separate the page tables. This means that there's no TLB, there's no virtual address translation that we can shortcut to the TLB from. And actually it turns out that hardware features of PSIDs are useful again. But all we're actually doing here is restoring functionality. And it's no surprise that things that look like this, while they cause us some of the greatest short-term pain, they're also ones that, Intel's already said that Cascade Lake, guess what? This one doesn't happen anymore. Because there was a notion of how this could be mitigated, and there was a notion of a boundary that should be enforced that wasn't. Variant 2 was interesting. So we came up with an interesting mitigation for this using kind of returns. It turns out that returns are a special type of indirect branch. They always pair with a call instruction, which means that, guess what? Hardware loves accelerated indirect branches. They put a dedicated predictor just for return, because they know that call is going to generate the return points. This has a useful property that you now have a predictor that you can use to fork execution, because you have the on-stack value that says where you're going to be returning to, and you have the RSB shadow, which is what the hardware actually uses to control the speculative execution. So by doing this, we could generate indirect branches where we could control both the retirement and speculative destinations. And obviously, because it only makes sense for a single instruction stream, these are per hyperthread, and we got everything we wanted. There was actually kind of an interesting development in actually doing this, where we kind of proposed this idea to Intel, and we knew they were all looking at it, and we knew we were all looking at it. But there was a period of time where we had no answer. And we knew that if Intel had found a reason to say no, they'd tell us right away. But it would take much longer to be able to say yes, because there's kind of they have to be able to stand behind that yes. There's a verification that takes place. So that we had our own kind of side channel here, where the longer that we went with no response on this, the more sure we were that it was looking viable. So as we had no response from them, we were already going and writing the compiler extension to do this, because it's if they'd been able to break it, they would have just said so, because that's the easiest answer. But if we look at what we've actually done here, this is kind of in between introducing and restoring, right? In some ways, we've restored a separation that you thought might exist between kind of user space and the kernel, or the guest and the hypervisor. But at the same time, we've also kind of introduced a new restricted speculation branch type, right? You can think of this modified instruction sequence as a way we've introduced to software that software can say, no, don't speculate on this branch. And this example is kind of right in the middle, where you would expect that maybe future processors widen the tag width or do something else to prevent this false sharing. But at the same time, we have been able to introduce something. And it's also interesting because the mitigation that Intel did at the time was purely inductive, right? They introduced a new the microcode introduced a new execution mode that restricted speculative execution. And a thing that turned out to be crucially important here was that the processor itself has a transition cost when we transfer between these kind of unrestricted and restricted speculation modes. And for us, that was actually the key cost here, because these operations happen really frequently, right? You might if you're thinking about something that's doing like web serving, you're making syscalls for every socket read. There's a really high turnover rate on those syscalls. So if you have to change the processor mode every time, it has this kind of dynamic cost as well as the static cost of all those transitions. And so as we think about how do we do this, how we manage that cost and where we pay a runtime versus where we pay a transition cost is a really important aspect. And this list keeps growing, right? And it's kind of a spectrum. On the right, you have things like Meltdown. You have L1TF. You have lazy FPU. For those who didn't see lazy FPU, it turns out that the FPU, you could lazily load and unload values. If you touched the FPU in a process that wasn't using it, you got an interrupt. But guess what? If you did that in the speculative path, just like the generic variant 1, you could speculatively use those values in that restricted space, even though you weren't supposed to have access. And if you did it in a branch shadow or some other speculative shadow, it never generated the interrupt because the hardware goes, oh, I misspeculated, and discards the results, even though the cache side effects are already there. But right on the right, you have these things where we have these things that the hardware has expressed boundaries for. We expect that Meltdown is going to be, while Meltdown and L1TF are kind of the biggest hitters in terms of the short-term impact, those are also the ones where we expect a generation or two out to be fixed. But as we go over to the left, right, as we start looking at things like memory disambiguation is saying, I can say these loads and these stores are independent of each other, and I can reorder them. Guess what? That speculates. It gets it wrong. But there's no boundary in the software at which we've said you cannot reorder across these boundaries. And so this is where it becomes really hard. How do we introduce these notions of security to software that hasn't had to do them before? And on the far left, we have variant 1. And I put it on the far left because it is really kind of the most generic idea of variant 1, where we're working in a single address space that doesn't have any previous hardware notion of separability. So, this is a luxury we don't have. We don't have page protections. It turns out that for browsers for variant 1, the immediate term approach was exactly this. They separated different websites, different tabs into different processes, and this was a way to introduce that boundary. But outside of the page tables, we don't really have a good construct for software to advertise this, right? And the key examples really are kind of these browsers with JITs and kernels and hypervisors and guests. And so while maybe we can use things like page tables to do it, the question is really, is the best way to do it? How can we introduce these things over time? And to kind of start filling in those points, really think about this respect versus introduce, as Jon and Mark both kind of talk about this from different angles. Jon's going to be looking at it from kind of the software angle, and Mark's going to be looking at it from the hardware angle. And with that, I'm going to turn things over to Jon. Thank you.
Okay. Do I get the clicker? I don't get the clicker. All right. Afternoon, everyone. My name is Jon Masters. I'm here from Red Hat. I'd like to thank Partha, Jon, and Paul, and Fix-It Felix, eh? Not been called that one before, so that's kind of fun. Okay, let's talk about the software implications. So what I want to do in my section of the talk is kind of walk you through some opinions on how I think we got here, where we are today, the process of mitigating security vulnerabilities, what options we have available, and then some thoughts, some specific mitigations that we've deployed, and then some thoughts for the future. So I've got a question before I get much further. Who here primarily identifies as a software person? Okay. That's actually more hands than I thought I would see today. So great, that's good. We're out there. This is good. But I think one of the key reasons that we are where we are is that we don't talk to each other anymore, right? If we ever did. Now, I recently saw John Hennessy's touring lecture with Dave Patterson, and they walked through
kind of the history of computing and then also where we're headed. And I'll touch on this in a few minutes. That there is this next wave of computing coming where hopefully we do all get to work together some more. But I'd like us to think, even now, let's think, it's crazy how we got to the point we're at. We never speak. We never plan things ahead with each other. There are exceptions, but what often happens is, hardware designers go and build some great hardware, and then we start talking about it. Or software folks say, that's hardware. I don't care about that. We have to stop doing that, right? That is a very bad thing. So if you don't know enough software people, go meet some more. And if you've got friends who are in software, tell them, hey, hardware people don't bite. And let's stop being one or the other, and let's all try to get along. So just thinking back in terms of history, how do we get here? Well, earlier hardware was much simpler, right? A lot of us grew up with much simpler machines. They've become much more complex in recent decades. And in the early days of computing, there really was this explicit ISA that we were programming to. We had a very strong understanding, or we thought we did, of how machines worked. As Paul kind of alluded to, the ISA contract was insufficiently defined. It was sufficient in the early days, but over time we added more and more layers that served to mean that what we had defined originally was not explicit enough. At the same time, programming became much more abstract in nature, right? Some of us still write code in assembly and C and so on, but many programmers today, many good programmers today, have no idea what a stack is, no idea what a branch is, and as we were saying over lunch, we can't just go and suddenly change that. That is the world we live in. A lot of software has been written in very high-level languages, and we can't just go and change that world. That is the reality that we're in, right? That helped build the amazing world that we live in today. But it means that there are many of these implicit assumptions that machines are sequential. They do things in this one specific sequence. And of course, with speculation engines and so on and so forth, that is not necessarily true. Now, shared tenancy has made that much worse. That has increased the attack surface dramatically. And a lot of the software that we built in that previous time has then been put into this much more dangerous world of shared tenancy environments. And, most of the isolation work to kind of constrain those workloads came a bit later. Okay, so on the hardware side, people who buy computers expect them to get faster every year, right? Jon Hennessy, who, I'm going to say this joke once, wrote the book on computer architecture, has a great graph. I think it's figure 6 in the book. And it goes through kind of the golden age of computing. We have this slow initial ramp, and then we get this 52% year-on-year growth in performance, and then it's been leveling off for the last few years because we've got all of the cheap wins, right? And many of those wins happened because of building capabilities such as out-of-order execution, speculative engines, and so on. And we treated them as these black boxes. Right? Software people, until fairly recently, many had never heard the term speculation. And a lot of the design choices that we'll go into today, they happen because we make assumptions. I handle a lot of my validity checking or my access checking or lots of these other things. I handle them at the end, at retirement, because it's a black box, it's not visible. And none of us in the software space seem to care about that. We didn't come asking, hey, where did all that performance come from, right? We're quite happy to take it as well. So we have shared responsibility for where we are. And then, as I said, implementations became more complex over time. Programmers have this understanding that everything happens sequentially. Paul touched on speculative store buffer bypassing or memory disambiguation as one example, where programmers are not thinking about how I might be speculating about the results of recent stores, right? There's a lot of things the hardware is doing underneath that we're not thinking about at all. And it turns out, this may surprise you, but programmers also do not understand hardware. During the course of the mitigation exercise for Meltdown and Spectre, there were many times that I spoke with programmers who said, well, they'll just ship a new microcode release and they'll fix it all in there. Everything's microcoded, right? Every instruction can be fixed, every little flow inside the processor. That's not true, right? As I would have to explain to folks, only certain logic has a microcode sequencer or similar structure underneath. And, we can patch some things, but we can't change, page table walkers. We can't change cache behavior, all of these things. And the same is true whether you're talking about an Intel or AMD processor with microcode, or you're talking about an IBM processor with millicode, which, it may surprise you, most people had never heard of until quite recently. Or whether you're on RISC-based machines using aggressive numbers of chicken bits and turning things off, right? We don't have infinite choice in what we can do. So to summarize, how did we get here before we get into mitigations? We have this us and them mentality, which has been going on for too long and has to end at some point, hopefully sooner than later. We are moving towards a new world in which, in order to achieve the kind of performance wins that we've been looking for, we are going to have to work much more closely together. And this kind of upcoming renaissance, or Paul pointed out that there's a lot of Brits here, so renaissance in computer architecture, it can serve to bring us a new hope for where things could go in the future. So now let's talk about mitigating specific vulnerabilities and what we do. So last fall, I wrote a little document inside Red Hat entitled Concerning Modern Microarchitectures, which started to capture some of the kinds of problems that Anders Fogh, as Paul mentioned, got very close to publicly revealing last July in his blog. And then those of us kind of in the know for a few months worked together, to try to figure out what we could do. Now, some of us interested in security research had read, papers, the prime probe attacks, the other cache attacks. I got very interested in reading Daniel Gruse's PhD thesis around this time, because he goes through all these attacks. We'll talk more about that in a few minutes. Throughout the whole thing, I think there were two takeaways. One was that people often labeled this as an Intel issue, losing sight of the fact that this was a cross-vendor, entire industry-wide problem, right? That graphic that you see there on the right, that is a mainframe simulator running over the holidays. So, in my capacity at Red Hat, I worked with at least 7 different microarchitectures on mitigations for these vulnerabilities. And that mainframe emulator there is being used to test Spectre variant 2 mitigations through patched millicode. Now, the emulator is not running millicode, but we're testing some of the software interfaces. And the other thing I found is that most people, even when we told them about everything we were working on, they didn't believe that this could be possible, right? I think Jan Horn is an amazing individual for challenging what we all learned in school, which is this is how the world is. And when you start to say, what if it's not? It is amazing how long we all miss this. And we would have to sit people down and we would have to show them, no, we're not, we're not full of something. This is really true. Look at this. So an example response strategy. So we had a specific timeline. That's actually a good thing, because you don't want these things to go on forever, trust me. You do have to have an end. But that means we also had a limited amount of time. We have various knobs and dials in the hardware. We have various things we can do in software, and we have to focus on finding something within that time frame. So, anyone here a Star Trek fan? Some of you guys are probably, right? So there's a term in Star Trek lore called the Omega Directive, which is about a molecule that's not allowed to exist, and all knowledge of it must be suppressed at all costs. So I thought that was a very fitting name for the team. So that's why we're called the Omega team. And we have an Omega Directive, which is you will not talk about what we do, except today in front of all you good people. But you can keep that quiet, right? You're not going to talk about it. And so we collaborated with industry peers. I work for one Linux company, but I will say that there are other great software companies out there, other Linux vendors, folks like Microsoft. We have had an amazing collaboration with lots of companies. And what we did was we came up with viable mitigations. In the case of Linux, we worked with other vendors to get them staged and ready for upstream kernels released by Linus Torvalds. And then we worked to get those backported into our vendor kernels. And of course, we also had to produce blogs, webinars, all of the materials for release at disclosure time. And the total engineering cost in Red Hat was very, very small for Spectre and Meltdown. It was only 10,000 hours of engineering time. That's that one initial January issue, not the recent ones as well. And L1TF has already cost us more than 10,000 hours. So what options do we have available? Well, these processors are deployed in the field. So we have a range of options. We can tweak knobs and dials. Maybe we've got some chicken bits. The average high-performance processor has about 10,000 of these today that we can tweak. But maybe we can't turn off any particular feature. Maybe the cost is too high. So in some cases, we can use microcode or millicode assists. Paul touched on the indirect branch restrict speculation feature that Intel added to their microcode, which we could use as one way of mitigating variant 2 of the branch predictor vulnerability. We have various options in the hardware. They do vary between vendors, but none of them are magic. And usually it ends up being a combination of hardware and software mitigation. Let's touch on Meltdown. So Paul walked through this attack a little bit, and Mark is going to go into some more detail, so I'll just touch on some of the highlights. There are two elements we need for the attack. We have to have a valid translation, and we have to have the data there for you to take. And so the mitigation depends on the architecture. So in some cases, we may flush the cache if we can guarantee that we need to have it in the L1. In one case, we actually just do a cache flush in certain places. The classic case that you've seen on x86 is page table isolation, formerly Kaiser, in which we tackle it through the first path. But it will vary across different architectures. Oh, the team you see on the bottom right there. So following the disclosure, I've had this opportunity to go and meet with all the teams that have been working on doing security research, and that's the Graz team. I'm sporting my Meltdown t-shirt there. Spectre variant 2. So we've got to mistrain the branch predictor. So as Paul mentioned, we can use his wonderful, glorious invention of Reptolines, which we did actually move to for mitigation over time. But in the thick of it, not being able to go and modify tool chains very easily and having lots of other constraints typical to traditional enterprise, we had to do something fast, and that meant effectively using these hardware interfaces either through microcode with IBRS, with magic new instructions that look like no-ops but actually do things, in some cases through millicode, and then also through other firmware interfaces. ARM uses a monitor call, an SMC call, to do similar. And what we did over time is we moved from one mitigation to the other. So we improved the mitigation. We moved from the microcode interface to Reptolines, for example. And there's an example of the kind of code changes we made on the right. So the focus of Spectre variant 2 mitigation is really about protecting cross-privilege boundary attacks. We didn't have the option to, we'd love to protect every case by default. Some of them can be very expensive. So our focus is to have a very safe default to protect user code and kernel code, protect the kernel from being exploited by user space. But some of the mitigations have opt-in elements to make them even more robust against all variants of the attack. So for example, you'll see on Linux a Spectre v2 equals IBRS always option, which more paranoid users can choose to opt into. And then future hardware is going to advertise, magic automatic mitigation or reduced cost to deploy mitigation. So on x86, you'll see Arch capabilities. On ARM systems, you'll see a new magic SMC identifier that will say, I'm fixed now. And on ARM, they'll change, on IBM, they'll change things like the device tree to advertise this hardware is not vulnerable. Spectre variant 1. Again, we're trying to focus first and foremost on the cross-privilege boundary attacks. For example, the malicious eBPF packet filter example. These mitigations changed over time. So we had a more expensive instruction stream serializing option at first, using fences. We later transitioned in the Linux kernel case to using speculative clamping to say, I might speculate here, but let me clamp the range to make it safe speculation. And then new tooling was created. So we've got scanners to look for Spectre variant 1 gadgets. We have new compilers. Google has a speculative load hardening LLVM. Microsoft has the QSpectre options to MSVC. These are all still being worked on. There's a lot more work ahead. And NetSpectre reminds us of the importance, the remote aspect of this vulnerability. Let's talk about last week's fun and games. So last week, the new L1TF, L1 terminal fault vulnerability was publicly disclosed. As Paul said, it was interesting timing for this talk, given that we knew this was coming. And it takes advantage of page table present bit validity speculation. Lots of these hardware optimizations are looking at valid bits. Anything they can speculate against, they will. So in this case, there's an attack where I can create carefully constructed page table entries, and I can use that to extract data if it's present in, for example, the L1 cache. And we've all seen that there's some exposure here. For example, in some enterprise environments, I may have to turn off Intel hyperthreading. So there's some cost here. And on the right there, you'll see a diagram or a screenshot from the very first time that I got a reproducer working for L1TF. Doesn't entirely work there. It's missing one character, but kind of got this working in March and really just saw the amazing need to correct that vulnerability as well. So each of these has a performance hit, of course, and testing these mitigations was therefore very challenging, in part because we were not able to tell everyone why we were doing it. So we would ship patches, and we had these wonderful cover stories that we gave. We said, well, we're just really keen on address space randomization, de-randomization attacks. We think they're awful, and we need to really, really fix them. So that fiction worked for quite a long time, and it broke a little bit early in January. And I think the other part of this is that the impact on existing benchmarks and tunings is significant as well. So a lot of those spec numbers, you're now going to have to ask yourself, when you ran those numbers, did you run them with these mitigations on? Did you run them with them off? There's a lot more here than just solving these challenges. So what's happening going forward? Well, of course, additional exploits will keep coming. We need to prevent fatigue as a result. Collaboration across the industry is important. We've built up some great contacts during the previous sets of vulnerability mitigation, and that's been very, very helpful. As I think many people saw last week, Unfortunately, we've gotten very good at handling these, or I think we have, and our L1TF mitigation kind of went off without a hitch because we've built up all of these great contacts. Funding research is very important. I talk to a lot of researchers who tell me that they won't get a paper published unless they can show a high-profile, high-impact, real-world example right now. So, for example, NetSpectre at first was not published because finding a real-world exploitable gadget was difficult. That does not mean it's impossible. That just means it's hard. So we need to really look at how we can fund research and draw attention to these issues. So where do we go ahead? Well, obviously we're going to get new hardware that addresses some of the issues. As Paul said, looking at Spectre Variant 1 is going to be a many-year journey. I've got some thoughts there about register, tagging, and tainting. I've talked with some of you about those. I'm sure that everyone has some ideas, but this is going to be with us for a long time, so we do need to really think about these as new classes of attack and really put the research required into the long-term mitigations. Changes to how we design software are going to be required as well. The onus cannot all be on the hardware community. We also will have to make some changes to how we build our software. Open source can help in this process, right? But open source won't magically solve all of our security problems. So I'm a big believer in the emerging open source architectures. I think RISC-V is a very promising technology, but magically replacing all of our processes with RISC-V processors will not solve the problem either, right? However, having open implementations on which we can collaborate and we can work together, now, that's very promising indeed. And finally, I want to leave you with a thought about all of the processes we do have deployed today. We have a lot of very closed, very undocumented behavior in these machines. We've seen a lot of attacks against microcode, against firmware. It's very hard to trust what you can't see. And with that, I'd like to hand it over to Mark.
Thank you. Thanks.
Okay, so I learned a new term the other day. It's called Spectre fatigue, as the Spectre bugs keep coming, and I hope it doesn't refer to my talk here as number 4. So I'm Mark Hill from Wisconsin. I'm also in my last week as an old Google intern. So I'm going to go over the background a little bit, but very quickly because the other speakers have done that. We'll talk a little bit about repairing the microarchitecture, looking at sort of the bigger picture rather than in the weeds where some of the talks have been, and then we'll sort of take the long view about what this might mean to architecture. Now, I'm a computer architect, not a security expert, and kind of as Jon Hennessy said at the beginning, that's really part of the problem. Like, how can you be a first-rate computer architect without being a security expert? Hopefully not so much going forward. So what's the setup? Let's take the long view here, right? So in the early 20th century, or really World War II, we started building computing machines in earnest. And every computing machine had a new interface to software because there was just no extra devices for indirection and we didn't have a good understanding. And so software had to be completely rewritten for each new machine model, and that was untenable. So beginning in 1964 with the IBM 360, we developed this notion of computer architecture, which I'm going to call Computer Architecture 1.0, which is the timing independent functional behavior of a computer. So that's the interface, that's what software is written to, and then now what's going to be called microarchitecture, we can go crazy in the implementation and improve performance all we want. As Jon said, the idea of covert timing channels have been around for a long time, the password cracking stuff in 10x. So much so that the US Department of Defense was very concerned about it even in the 1980s. One process to signal another by modulating its own system resources to be observed by a second process. I knew about this, but I really thought it was like a spy versus spy thing, that if I wasn't involved with state actors, it wasn't my concern. And obviously, I don't believe that anymore. So speculation leaks protected information, as we discussed, and we'll talk a little bit about why it's essential performance. I'm going to argue that these are not bugs, because you can argue that these implementations are completely correct to their specification, Architecture 1.0. And so that really the problem is there's a flaw in how we specify. And we have to think about how we're going to be able to do better. So what are we going to do? Well, the first thing we're going to do, and you've seen a lot of examples of that already, is we're going to repair the microarchitecture, you're going to restrict the software, you're just going to deal with things one at a time. In some sense, we're going to manage, and we're not going to fix like we do with crime. But I think ultimately, this problem has been decades in the making, and it may take a while to fix it. We should figure out a cleaner way to define these architectures, because it seems like Jon and Paul are happy to know tons about return address predictors, et cetera, but it doesn't seem like such a scalable solution. Okay, so we're going to just skip this because this was well covered. All right, so some people say, well, I never heard of speculation, and well, why don't you just get rid of it, okay? So first of all, modern processors do a lot of speculation. So this is from Skylake, 224 instruction reorder buffer, 14 to 19 stage pipeline, 3 levels of caches. We often don't think of caches as speculative structures, but they really are speculating that things that you've recently referenced or what near recently referenced you're going to reference again, and they handle it much faster. They don't have to have this undo capability. And there's also speculation in the interaction among cores. You speculate that current coherence is good, you speculate there's no bank conflict. And these are not just restricted to high-end processors. We heard a talk this morning on the Samsung M5, where the processor that's going to go into a phone was, the first order up to these kind of numbers. And also the Berkeley processor was some distance to these numbers. So when you want to just get rid of it, well, it's going to cost you many integer factors of performance to just get rid of speculation. Like, I'll throw out this number 20x. It's like moving back to a 200 megahertz processor. Now, let's not argue about the number, because we're not going to do this, because it's not viable for any general purpose processor product. We're going to have to figure out ways to more creatively mitigate these timing channels, and we'll talk about that. Okay, so I don't know if this number was put up, but Meltdown leaks kernel memory at 500 kilobytes per second. People always knew there were side-channel attacks. Ruby Lee over here has done a bunch of work on that, but I just thought, you get a little bit. Now, what's really happening here? Well, my take is that you're going to do this load from user space to the kernel. This load is eventually going to trap. Nobody says when you have it trapped. And so what you do is you let the load happen, you prefetch into the cache, and then at the end, you take action to make it trap. Completely legal by Architecture 1.0, and you get high performance, but you get meltdown. A lot of other people have such a user space load to kernel memory trap early. That's also okay by the architecture, and you don't get meltdown. It's relatively easy to do because you have to do address translation to do the load, and when you do address translation, you look at the PTE, usually in the TLB, and it has the protection information. Okay? And so what do? Well, going forward, you make sure that address translation fails, so you can't do this prefetch, and that gives you what you do is you don't map the kernel, and that lets you, you have some performance loss from syscalls, or you make your architecture trap early, and Intel can join the others. And this is, in retrospect, an uncommon case where it's really easy to stop speculation early. Usually when you're speculating, you don't find out to the very end that you've done something wrong. This is a relatively easy case. So it would seem like we dodged a bullet, but you guys know that's not the case. Spectre has all these variants. The clear problem is that the hardware doesn't really know when you're looking at something that's sort of near you or something that's different, that you're going from the sandbox into the browser. And it has many variants, as already discussed. so I won't go into, but the more scary thing is you might not know about the write buffer bypass one. There's things that you can do with coherence, with functional units. Last week there was page tables. I think we can be firmly established that we're not out of Spectre variants yet. And so it's really hard to mitigate all of these, and it's particularly hard to mitigate the ones we don't know about. So for performance, we seem to need speculation, but speculation results in Spectre variants. So what do we do? Okay, so the first thing we're going to do is we're going to repair the microarchitecture. So let's step back, because I'm a propeller head academic, I got to do this kind of thing. There's this universe of computer behavior. And if you have a specification that says, out of this universe, you got to do this more restricted set of things to be my architecture, okay? And then a given implementation refines the specification even further. Say the specification allows a write buffer of any size, your implementation picks a specific write buffer. Okay, and a different implementation does a different thing. Here's an implementation that includes behavior not in the spec that has a bug. Okay, now what's happened here is that this implementation B meets the spec, but it leaks information. It fails to be desirable. And so what do we do? Well, repairing the microarchitecture says is somehow what we want to do is coax B and make it C so that it's within this green circle. Okay, and so how are we going to do this? Well, we can't just turn off speculation, and so we have this algorithm here. Find timing channel with concerning bandwidth, fix it with performance and complexity costs, repeat, maybe forever. This is not easy, so let me pick on one particular example. So way partitioning is a well-known way to, if you have two processes, one which may be a cache pig and one which is performance important, you give them different ways in the cache, and this way the pig doesn't disturb the other one. Intel's CAT technology is an example. Well, this sounds like, hey, this already there. This might be pretty good for also breaking the side channel between these two processes. Well, no, it's more subtle than that. You also need changes to partition the replacement algorithm. You need changes to avoid shared hits, etc. This is not a problem with Intel's CAT technology because it wasn't designed to be a security feature. But to be a security feature, you have to do more. And there's a new paper by Joel Emmer and others ingeniously called DOG on this. And the reason I mention this is that, just what superficially looks sufficient may not be. And so this approach, as I hinted at before, is really managing without solving. Even our politicians today, who are often untethered to the truth, they don't even campaign on we're going to eliminate crime, right? They worry about, well, we're going to minimize costs to society, which they don't think this way, but I would think this way, which is the cost of security, police, et cetera, plus the crime cost. We minimize this total cost, and that's what repairing the microarchitecture could do. Let's see. So what are the things we do? A lot of things have to do with isolation. If you have a channel, you want to just make sure you can't channel. So we no longer share branch predictors among hyperthreads, BTBs, etc. We partition caches. So one part of the cache could be used for the kernel, the other cache for the user. Of course, partitioning has the age-old, where do you draw the line? And if you draw the line wrong, you lose a lot of performance. You can also flush. Reduce aliasing information. Some of these tricks, got high bandwidth by being able to put data values essentially into the cache index. You have a fully associative cache, there's no index, but as we know, there's power costs. We can randomize. My understanding with randomization is that it helps, but it doesn't help as much as you think because people can retry many times and sort of take the average. We can do more hardware protection. I think this has a lot of potential, as was talked about, trying to turn, well, the way I would characterize it, let's say we would trap when the JavaScript accessed the protected browser. Right now there's no trap. But if we can put a trap there, then maybe we can turn one of the Spectre variants into Meltdown. And Intel memory protection keys that are coming out, they could be useful, assuming that the processors didn't speculate past the protection keys. And there's possibilities of undoing speculation. So what is this all sort of leading to? It's leading to, can you get more toward constant time execution, really constant power execution too? Where I come from, there's a legendary coach, Vince Lombardi, who somebody once says he treats us all the same like dogs, right? We know how to do constant time execution. We just go really slow, and it's constant time, but that's not so viable. All right, so what we want is high performance, the red thing, and we want safe, the green thing. And are we going to be able to get it in the same thing? People are hoping that there's this happy knee. I'm a little skeptical. I think, we try to get both of these things, we might get neither of these things. And this is a particularly bad time to hurt performance because we're not getting the wonderful doublings of performance that we've had for the last couple decades. So what to do? One idea is to bifurcate. If you can't have it all, choose. So in time, you have a mode where you're faster, a mode where you're safer. You disable some speculation, not always, but when you want to be particularly safe. We can also bifurcate in space. We can have some cores that are higher performance, some that are lower and much safer, and in particular have memory systems that don't interact in fancy ways. And this kind of plays well with dark silicon, where you can't have everything on at the same time. And maybe we can bifurcate from use, where you have certain things where you, if it's really important, you don't allow other things close. None of these are great, but they may be better than hoping for the magical solution that's both high performance and completely safe. All right, but let's step back for a second and look at sort of the big picture, the decades-long picture. So I showed this before, that we were going to somehow coax implementation B into implementation C that's now in the green circle. Okay, but why do we know that C is safe, and that's because, well, what we need is an architecture 2.0 that says, hey, here, this is something that refines the original architecture specification, but also doesn't leak information. So we ought to define that, because then we can judge our implementation of whether it meets that new, more rigid standard. That's good. The only problem is we don't know how to do it, right? So if we're going to make this 2.0, is it an abstraction of the timing visible microarchitecture? I mean, you saw these guys, they're happy to know all about the things that are beyond the Hennessy and Patterson text, right? But that's not going to be viable going forward. Lots of software people can't do that, nor do we want, architects don't want everybody to know about things because we want to be able to change things. Are we going to somehow say there's going to be a bandwidth of known and unknown timing channels? Are we going to enforce more limits of user behavior? Well, it looks like you can map the kernel into your address space, but you can't. And how do we specify those? And there's many possibilities, and we just don't know yet. None of these things feel good enough to me yet. But I predict that I speculate that there will be dozens of papers on the subject. I know one of you guys were worrying that it's hard to get these kind of security papers into conferences, such as architecture conferences. I predict that restriction will be reduced. Now, one sort of interesting compliment right now is that we're no longer relying just on general purpose processing, which is so speculative, but we have other things called accelerators. Even if they're not always faster, they're sometimes just lower power. And they have properties. This is from Hennessy and Patterson's taxonomy. But the key thing about them, I guess I should explain this picture first. The flat purple thing is the general purpose CPU, does everything but fairly well. The accelerators tend to do one narrow thing particularly well. And the key thing for the purpose here is that they don't really rely on speculation as a first order feature. Okay? But in general, though, they're not timing channel free either. They can have branch and memory divergence, such as a GPU that's sitting on your memory bus. There's always talk about formal methods, and there are things that have great potential. By the way, this is Euler's equation, has nothing to do with this formal methods, but I've always wanted to use it in a talk. And you can do things statically, but by the way, dynamically, it's really hard. I mean, there's a theoretical proof that by looking at an individual execution, you can't even tell if it leaks information. You have to look at sets of information and see sets of executions and see how they look at things. And I don't know, statically, can we do it and still have high performance? Maybe if we bifurcate. And then finally, we need to have a spec to check against, right? You need to say, this implementation, doesn't leak information. And, well, you can't check against a spec until you have it. Okay, so open architectures have been mentioned a couple times. Security experts don't like it if you just hide everything and hope that's good. They like to have many eyeballs on the mechanism and then, let's say, hide things in the keys. For open source software, it can help, but more eyeballs on a bad implementation, it's still bad. And so for going for hardware, open interfaces can help, and even open implementations help. There's more eyeballs, but there could be Trojans hidden in them, and we'll see. Optimistically, David Patterson says that most future hardware security ideas will be tried on RISC-V first, and I think that's true because it's one of the more real things that's easy to get out there, so people will try their ideas first, whether or not they move them to a proprietary architecture later. All right, so as Jon was saying, we should talk. I'm a computer architect and not a security expert. In the 20th century, we definitely had these layers following on the Roman legion, divide et imperia, divide and rule, and it was very low bandwidth. The security people that also did hardware, for example, is a relatively small community. And in the 20th century, we're going to have to talk a lot more, not just for security, but also for performance, because the performance is not going to be had as easily as it was in the 20th century. So in summary, as we know, we're leaking this information, and in the short run, we're going to repair the microarchitectures, but the long run question is how do we define this right so that we can potentially eliminate the problem? Or are we forced to just make it like a crime thing that we're always mitigating? And it'll take a long time, I think, to resolve where that comes down. Thank you.
Okay, I'm going to invite all the 4 speakers back to the stage here for the panel. I thought that was pretty exciting. I think this is the first Hardships keynote that I know of, led by a Turing Award winner, and we had Fix-It Felix here as well, and an Euler's equation too, from what I can see. So the way this is going to work is please come to the microphones, introduce yourself. We have plenty of time for Q&A. We have about the next 20 minutes for a panel discussion.
David Cantor, great talk, gentlemen. Thank you very much. So right now we're talking about bugs that are not bugs, but we are talking about security issues that are fundamentally digital. But there's been at least 1 or 2 sort of more analog bugs recently, specifically rowhammer. Do you have any thoughts on that and how that can fall under sort of your rubric of modern or architecture 2.0?
Oh, that has to be me, huh?
No. I was just using your phrasing for it.
I like the phrasing. I don't know if I have a good answer for how to classify rowhammer. I mean, it's a class. I mean, we have this abstraction since Alan Turing and before of the digital abstraction, and sometimes the physical world just interferes with us. Mm-hmm. And
put ECC everywhere. It's magic.
I'd say we actually did see last year someone attack rowhammer via speculative execution via the GPU with glitch, right? Mm-hmm. So there definitely is overlap here. For me, I do liken that more to kind of when I had that spectrum of where we're introducing new features versus trying to respect things we thought were there before. Rowhammer for me is very much towards the right end of that spectrum. Even when we were looking at it, how can we fix this in software? How can we fix this in hardware? We did things like double refresh. And once we had that, we were kind of back to our status quo. And I think that's what you'll see with things like Meltdown, where like right when it comes out, these ones that break the implementation but not the spec, they create the biggest short-term pain, but they're also in some ways the easiest to mitigate in the long term because they tend to be something specific we can close the door on. And once we're on a chip that's closed the door on that thing, we're often past it, which is, I don't think, the case for variant 1. Mm-hmm.
Okay.
Hi, Herman Schmidt from Google X. Does anybody care to speculate on what are the societal fixes for who bears the cost of this? Assuming that this is just like, you know, the frontier of a continuous cascade of security issues that have to be fixed. Right now we've got Intel and Google and Red Hat, well, 10,000 hours, not too much, but you know, they're bearing the cost of this. But as Mark points out, it's a societal cost and figuring out how do we balance this. Any thoughts on how we should fix this long term as a world?
Well, welcome to an industry where you get a 25-page disclosure that's your warranty that says nothing is warranted about this product, and if it doesn't work the way it's supposed to, that's too bad for you, right? Imagine if your cars operated that way, or if medicine you bought from the pharmacy operated that way. So I think there's a redo. This is not just about this particular problem. It's about a whole set of things that we have to change the way the industry works. That's going to take a long time. That's not going to be easy. And because software, we as a community have opted for functionality over other properties that are perhaps becoming increasingly important. We're going to have to change that. I remember many years ago when Microsoft still had competition from Word, from Perfect and other companies out there, Bill Gates complained vociferously to me that what would happen is the magazine writers who were doing the reviews of these products and telling people what to buy would make these checklists of how many features they have. Mm-hmm. And the user community would go out and buy the word processor that had the most checks next to it, not necessarily the one that worked best and had the least number of bugs. We need to change our whole perspective on that, because I think some of that thought still lingers many, many years later.
And you see it today with when you go and have a review online of a upcoming processor, right? The first checkbox is not how secure is this against some kind of side channel attack. The first checkbox is how fast does this run spec whatever, right? The security thing.
No, it speculates really fast.
It speculates really fast on spec numbers, right? But it, you know, a year ago, no one here, unless you're lying, and that's fine, would have said, oh yeah, I'll trade more security and I'll lose performance, right? It isn't something we've asked until much more recently.
And I think I would add, even today is kind of important in how we're responding to these issues, in that the last 12 months has really been this kind of desperate reactive thing, where how can we kind of go back and put these barriers in that we thought were there before. But you know, we're here today, we're talking about, as a group, how can we introduce the notions of these protections for software? How can we get the hardware, and how can we get the software working in concert? And that proactive mitigation is what's going to take us through the next 24 months. Even if you look at what companies have did for L1TF, it was much more general purpose than what was done for Meltdown and Spectre, with kind of the expectation that this is Pandora's box. There's more coming. So we can't just kind of, you know, plug that hole and move on.
I would also say on the cost front, so it's not just, you know, I said in my company it was 10,000 hours, but I think the other thing is we are suffering from fatigue for these issues. And I think that the more that come, you know, it's very easy to say, well, I had 10 this week, and I'm an admin, let's say, right? Which of those 10 do I really need to care about, and which are a bit more speculative in nature, right? And so that's a concern. That's also a concern inside these organizations. You know, we're having to make very tough choices. Do we want to add feature X, Y, or Z to the next product, or do we want to fix every outstanding possible security side channel? Of course, the second thing comes first, but it's not cost-free.
I think the other thing to remember is, while these are really important, the number of security holes that regular users create and tolerate, either because their software is not correctly configured, they don't do updates regularly, or now I want to know how many people out there change their passwords every month, use a different password for every system, have at least 14 letters or characters in their password, and always use dual factor. If anybody raises their hand, I'll not believe them. But there we go. I mean, you know, we have to get people probably to take security a lot more. And this balancing of security and ease of use is fundamentally a really hard problem for the industry and for users.
I mean, if from Mark's from Mark's last slide. If I could get my parents to stop downloading executable code, that would be wonderful.
Well, stop sending it to them, Paul.
You sent me this invite to this party. It looks so good.
Okay. So
It said from John.
Yeah, he said, a
So
note
just-
from Paul, I'm stuck in Africa and I need you to send me $2,000 quickly.
Okay.
Tears in my
just
eyes.
a reminder here, the talk is being recorded, so Paul, your mom is going to be watching this sometime. So,
If his mom's watching, don't download it, okay?
I have to show her how to click it first.
so while people are lining up, I wanted to ask one question from the panel here. Open source hardware. So I'll probably start with Mark, and I'd like to have the panel's perspective. Is open source hardware the answer to all the problems here?
Oh, absolutely not. I mean, it's an interesting phenomenon that's out there, and I think open source hardware is going to develop because we want to do hardware software co-design for a number of things, and what we saw in the software-only world, is having open source software lets innovation happen much faster, and so we're going to see open source software principally at the low end where you just need any processor, and it's a way to try out security ideas and get more eyeballs on it, but if somebody does a super complicated implementation, you may or may not be able to see security Trojans in it.
Anybody else?
I mean, I think the other advantage is that you don't have to worry about non-disclosure or anything else. It's all public. It's all public data, and that makes it, certainly lets the security guys put a lot more eyeballs on it, and people can look at it, and that makes it better to look for
But
flaws.
I would say that I think there's too much value add. I mean, but I say this in a good way. But the fabrication of a CPU, even if we had a totally open source spec,
Yeah.
there is so much that goes on the fabrication that that will never, that is always going to be secret source because it's worth so much money. And so many of these problems arise from challenges in those optimizations which are made in the implementation rather than the spec. So I think it's important that we think about how we can have a spec for delineating these kind of security principles within single address space contexts, within an operating system, within a hypervisor. But, and that's where it comes to like the specs today don't have anything for this. And I think that's where we need to see this kind of 2.0 that Mark's talking towards, where we need to have some way of expressing this intent, even if the hardware sometimes gets it wrong.
I think there's two other sides to it. When you have an open implementation, so again, we want to separate open ISAs from open implementations. In theory, you could have an open implementation of an existing ISA. I don't see that being likely for many obvious reasons, but it could happen. I think if you have a implementation out there that researchers can collaborate on, they can also try not only new ideas. So Chris, are you here? Presented earlier, and he's presented previously on a number of sort of ideas for how to mitigate Spectre in hardware designs. You can put them out there, people can try them out, that's great. They can also try deliberately implementing vulnerabilities. So you can have a class and you can show them, oh, I'm going to go ahead and implement Meltdown, right? And you're going to look at why this is a challenge for future designs. So actually having something that we can collaborate on across organizations, I think, is very useful as well as a teaching tool.
Okay. Yes, sir.
Hi, my name's Donald Forbes, Starlight Associates. I got a very strong interest in the compiler side of this back 2-3 years, really. The thesis I started with was that decoration of code was really the answer, because I then got stability of what's happening inside the compiler, and it was as simple as that, actually. What I bid for here is any open discussion of how to do actual decoration of either code or architecture, such that we can actually instrument the code as it's behaving. I think that will mitigate quite a lot of the actual problems. Beyond that, open, and I'm here for 2 days. So thank you.
So I think you're asking, it was hard to hear up here, I think you're asking
Annotations in the
how can we define kind of security principles within our execution flow?
Yeah, basically with detail, yeah.
So, I mean, the canonical example we have right now is separate address spaces, right? This is site isolation. This is how Chrome did variant 1, and it's how the other browsers are kind of following suit. It's how you're seeing some of the hypervisors handle things like L1TF. But this is a pretty heavy hammer. You could certainly imagine that all we're actually trying to get at with a separate CR3 is we're actually trying to get at the underlying tagging in the hardware, right? We're trying to say these cache entries are tagged with this CR3. And you could definitely start to imagine that you could add extensions where maybe you got some user control bits that got blitted into that mask that would let you say, the cache lines that I touch within the JIT and the cache lines that I touch within the JIT browser have this kind of hardware tag boundary between them. And that's certainly one of the kind of things we've thought about in terms of proposing. And that's really kind of why I was trying to frame this in terms of how can we introduce this, right? This isn't something that exists today. We could try and use the page table to make it respected, but that has a heavy cost. What we really want is kind of, and if you bypass the abstraction around it and go straight to the implementation, it's almost just like, yeah, we want control of those tagging bits. We want some way to have an abstraction at the higher level that maps down to the abstraction at the low level. And that's just not what we have yet today. And that's why we need to be proactive and start thinking about how do we get there. Because it's not going to happen for a few generations, but we need to make sure that it does happen.
I've told a number of processor companies, both when they've asked for feedback and also when they haven't, is that we have these sort of implicit separations. So CR3 on x86, and writing to these MSRs is expensive, both for implementation reasons, but also for optimization. They're not intended to be written very often, right? But what we need to have, I think, in future ISAs is subcontext as part of the ISA. If we want to go down that path, you want to say, this is code that's meant to be in a sandbox. This is separate from the actual code running that sandbox environment. Today, we have no way of tagging and actually identifying these environments. We simply have, implicit extensions of, say, CR3, separate address spaces. But that doesn't that just means a separate address space. It doesn't actually imply the same thing as this is a deliberate separate execution context.
Before we move on, I would actually love to hear from Mark on this topic, because kind of the two software guys have said, here's how we'd love to tell the hardware how to do it.
We know best.
What does Mark think about how the software could ask the hardware to tell it?
The question is, what do I think?
It's kind of, if you have kind of a stream of execution, how do you have that execution and the hardware agree on kind of what's a privileged and non-privileged context within it?
I think we're on the same page, so to speak, is that we need to have, mechanisms that express what's in, one space and what's in another space. And they need to be lighter weight than virtual memory address translation if you're going to switch back and forth in a user fast.
Yeah, I mean, this is what we saw with the microcode mitigation for variant 2, right?
Yep.
It was effective, but really expensive because those transitions happened really quickly.
Right. And that register write is not intended to be done, so when you touch that MSR, it's expensive.
Right. Okay. Ruby?
So I'm Ruby Lee from Princeton University. First, I want to say I'm delighted that you guys, Jon Hennessy especially, called this the era of security, because better late than never. I've been saying, let's design security-aware processors for the last 10, 15 years, 20 years. But this is really important now, so it's good that we are looking at it. Secondly, I want to say, Mark, it's really good that you're taking this attitude of not just fixing one problem at a time, because that's what the security community has tended to do. When there's an attack, they quickly try to find a fix. But in computer architecture, we need to look ahead, look at the bigger problem, and see if there's some principles by which we could design. And I would like to suggest that ISA 2.0, the first principle could be very, very simple. It could be something that security people have known forever, is Security 101, no access without authorization. If you can just believe in that and implement that in all your performance enhancements, it will get rid of a multitude of bugs. Okay, so I think there's hope yet, and the thing for us educators is, how do we now change the educational system as well as the conference paper accepting system to look at non-quantitative only papers that really suggest principles rather than necessarily only measure incremental performance improvement. I think that the challenge...
Maybe, sorry, was that question addressed to John, or?
I think that it's more a comment.
Okay, so maybe John can take a stab. I think we are asking about the educational implications, so maybe John, you can start with that.
Yes.
Yeah, so certainly I think Ruby's right that we need to do a better job of this. Let me point out that this is not easy. Mark alluded to it, but I'm sure a number of you have worked on verification of SMT processors or verification of cache coherence protocols. You want to have something that's really tough? Verify that your cache coherence protocol always does the right thing and never deadlocks. That's really hard. Well, now, think about verifying that you never leak information on a hardware structure that's shared. It's going to be extremely difficult to prove that there are no holes here. And I think that's going to require a new set of verification tools and approaches that we can use. But it's hard. And Ruby's right. We've got to educate students to understand it and work better on it.
But I applaud the idea of having a very simple principle, like no access without authorization. But then how do you get from there to the implementation, right? You could easily believe the implementers of these systems thought that they were doing that.
Yeah, that's exactly what they thought they were doing, Mark. That's exactly what they thought with the rollback on misspeculation. That's exactly what they thought.
Speculatively fetched the load byte during the speculative.
Of course.
We know now.
We know now. The problem, Ruby, is the definition of access.
Yes.
But I would argue that you couldn't directly observe the value of that, right? You had to observe it through a side channel. So it's a question of how to define access.
Yeah.
What do you do about lots of other things like prefetch, which when prefetches are wrong, they're supposed to just get garbage back, right? So there are a lot of issues like that.
Sorry, so I'm going to keep moving things around. I see 3 more people, and we have
more
8 more minutes.
Yes,
So
the only thing I want to say is you have to decide whether the cache is microarchitecture or architecture.
But that's a big change, making it part of the ISA.
But I think
CL flush.
But I think the other thing, just to put one comment with 2 comments there, in the computer architecture book, going back, every edition, we checked it. Appendix B actually starts to allude to needing to solve exactly this for caches. There's a number of processor designers out there. I jokingly said I wanted to send them a copy of this, right? It's been written down for a long time, not called out, but this is not a new thing to think about. It's just this has drawn attention to it.
Yeah.
The other thing is, don't dwell too much on caches as side channels. There are tons of others in there, and we'll fix all the cache issues, and we'll have TLB issues. Last week we saw one with page table entries being speculatively pulled in. There's tons of others out there.
So are there people waiting there? Oh, then please come closer to the mic so I know you're waiting, not hovering there. So go ahead.
So I just wanted to kind of back up and ask the implications of this on kind of the public cloud infrastructure. Is this essentially you're going to have less performance per processor, Intel sells in more processors and they're happier, or is this something where you start to diversify your processor? How do you actually think of that? Or is this just the price of a VM goes up because now you want exclusivity on average? Or how do I think about that shared architecture and kind of like the economic implications?
Well, I predict there's going to be some bifurcation. You're going to have to pay more if you want it perfectly secure.
Ultra secure.
And that means no one else is running.
I mean, I think it's really important to remember the slides where this is not an Intel-specific issue, right?
Yeah.
These issues are generic to how we've done modern microprocessors. And it is certainly true that operating systems and browsers and cloud providers are going to have to find ways to isolate more host state and processor state than they previously did. It's not actually clear that this is going to have a kind of catastrophic cost impact. But it is a new way that everybody has to be thinking about these problems.
Mm-hmm. Yep.
Okay, so I see we have 6 more minutes before the break, and I see 6 people here, so I'm going to encourage people to be crisp about the questions, and maybe the panel as well can kind of move things around a little bit. So I know gentleman has been waiting for a while. Go ahead.
Richard Traubin, Wave Computer. I've got a question. John began with talking about 3 attributes: leaking, transmission, and extraction. Seems to me the real problem is the tree has fallen in the forest and anybody can read it. So we're missing a tag, we're missing an identifier about the context that
has permission, isn't it fundamentally that we're not broadcasting and identifying who can reference the information that has already been deposited in the forest?
Well, I think the fundamental problem is that modern computers share data from multiple address spaces and multiple users, and they're sharing the cache, they're sharing the branch predictor, they're sharing everything all at once. And therefore, to the extent that information can leak across those boundaries, that's where the real problem is. And that, given that we write code now with lots of processes, much higher process. In the old days, process switches used to be so expensive that they rarely happened, and computers were very slow. But in modern computers, we can't do that. So we've got to find a way to cross that boundary while protecting the information we need to protect.
Okay. Yep. Sarah Biabani, GridCom. As a computer architect, at first I worried about optimizing performance, and I worried about minimizing power, and now I've got to worry about security. And we have security architecture. So my question is, what do we do next? We've got to perhaps get an IEEE standard, open a PAR, and do the shared knowledge that you have, requirements kind of a thing.
We communicate. Like, we have the software and the hardware actually communicate about what they're trying to do. We stop having the software say, I'm going to build a software sandbox. We stop having this hardware say, I'm going to build a hardware sandbox. We have the two teams work together and say, here is how I'm going to establish the boundaries, and here is what I expect those boundaries to provide.
Before we build I have a question. So if you had heard that the processor was speculating past a user kernel trap, would you have raised a red flag?
That generally doesn't happen. What you're raising there is actually that the cache has been bolted on as a side channel accelerator. The processor still actually has the trap early behavior you described for the page fault. It's that the cache is this kind of almost like a side accelerator that runs on ahead. And it goes, oh, I have a virtual tag. I can look ahead.
I will note for the record that the conversation between hardware and software is happening at Hot Chips right now as we speak.
Yeah, exactly.
So I think the question was probably about what are the forums where you can have that.
Right. My question was not that. I agree. You can discuss it, in certain conference rooms, but I think for the industry, we need to codify it. We need to have a method to get the information out, and the APIs defined and so forth. And to me, the cleanest path seems to be have an IEEE standard. We had, IEEE 754 when we had problems with the floating point error messages. Remember that? And so,
yeah, I think we absolutely should develop standard ways of doing this, but we can't do it by fiat. We don't really know the best ways to do it. So I think there's going to be a little chaos for a while. We don't want to prematurely standardize on something.
Okay, Jose.
Jose Renau, UC Santa Cruz. One of the things I believe what we should be doing is try to avoid time-side channels due to speculation on the processors. And it will take time until we'll get there, we'll go there. But I'm curious who in the panel, each one of you, who thinks that we should have a CPU that completely avoids time-side channels, speculative only, in the long term?
I don't think you'll see any hands.
Well, I think we should have some CPUs that completely avoid it.
It can be an enabler.
Especially in the dark silicon era, we can have a CPU over there for running the super special stuff.
Yeah, it's a little tricky. I mean, there's an interesting result that shows that the one thing that actually is power efficient is speculation when combined with simultaneous multi-threading. It's the one thing that actually is power efficient. Most of our speculation is not power efficient, but that's one that is. So, and of course, that's a primary leakage channel.
No, but I'm not saying to not have a speculation. I'm saying to avoid the side channel of the speculation. So you can speculate and keep it in a buffer and then kill it. Or you can flash caches. You can do a lot of things still having speculation.
There's a lot of side channels, and proving that you've got to close them all, I suspect is impossible.
Okay. Question from there?
My name is George Haber. John, I was in the Spark arena when you created MIPS. I think we are approaching this the wrong way. When the philosophy of RISC was born was keep it simple and as fast as possible and put on to the software the onus of making it secure. And we should go back to that philosophy. Everything you guys are doing is extraordinary. We should use some ML and AI to find every possible hole at the low level. But then, just like with airport security, instead of checking every baby and every woman and presuming that everybody's a criminal, if you do like the Israelis, you focus on the few that could be criminal and presume that hardware will be broken and I can steal any data from any computer by inducing an ECC error on the memory and reading out the whole damn memory.
Yeah.
And focus then on the software, who has the right to take the quote-unquote stolen data and put it somewhere.
I think the problem is scale.
Yep.
The number of attempts to break into machines at Google or at Stanford exceeds the number of people walking up in a day, is more than the number of people who pass through TSA checkpoints in a year. So that's the scale. You're being hit by attacks. And if one of them gets through and exploits one of these holes,
we can, in addition to that, I completely agree, but I think one thing we can do from a software perspective is build, try to have some level of detection where we say, this VM is looking very malicious.
Yeah.
I'm going to move it amongst all the naughty children in the corner.
Yeah, this is going to happen.
We can do some of that, but
instead of slowing everything down by 20x.
So hang on. There's two things. One is this certainly gives definition to kind of profiling high-risk instructions, but the second thing is...
That's a lot of CL flushes you're doing right there. I'm not sure.
The second thing is, the thing that's really hard about this is you can hide all of this in a speculative channel, in a speculative shadow. And as soon as you put it in a speculative shadow, the hardware has it's not like a person. It can't look at it and say, oh, that was a bad idea, right? All it knows is it went down a bad branch, and it did some stuff it probably shouldn't have done. But there's no way to prove in hardware that it was tricked into going down that bad branch, right?
Exactly right.
You can, as the user, I can completely control the rate at which you explore that alley. And so I'm very dubious of any kind of profiled or sampled attempt to mitigate this, because there's just too much that I can do to control and observe what you're doing in response, right?
Okay, last two questions here. We are 2 minutes. I know we are eating into the break. I'm sensitive to people being hungry, I guess.
We don't want to be in the break.
Vijay?
Vijay from Harvard University. One key thing that kind of really concerns me about everything I've heard for the whole past hour is that everything is kind of centered around the CPU. But John, you and David Patterson made it very clear that we were going to be looking at accelerators over the next decade. That's the only way we know we're going to get performance. So can you comment for everyone? And what are the implications on security as you start looking outside of the CPU, from the CPU, GPU, TPU, XPU, IPU, whatever you want to throw in, right? What are the implications of the bigger picture?
Well, currently most of the accelerators are single user mode, so you basically clear all the state. Now, whether or not that means you clear all the state all the way out to the memory system and other observable things is going to be a question. But I think you at least reduce the boundary for attacks and the bandwidth that you could suck data out. But obviously, if accelerators become pervasive, we're not going to be able to keep this current mode that the current ones are in, which is that they're single user. We're going to have to figure out how to make them shareable and process switched and put protection boundaries and do all those things. And that could well be what happens in the next 10 years in computer architecture.
One of the things side day jobs of mine is working on cache coherent interconnects for accelerators. And we've had exactly these conversations about not building Spectre accelerators that you're now in your data center, with your FPGA in the cloud. Sorry, in the cloud man, I have to say that, right? And it's sitting there and it's busily helping you to accelerate these. So we need to be very careful.
And the one thing I'd also add there is, like, when we say CPU, what we mean by that CPU boundary has kind of greatly expanded over the last few years, right? You've seen the North Bridge, which used to be a totally different chip, moved entirely inboard. You're seeing SoCs, which everything is in the processor. So when we say CPU, we don't just kind of mean kind of your execution context in your register file. We mean kind of everything that's hooked up to the socket, which is getting bigger and bigger in no small part because of how important this latency is, right? Because these latencies are minimized, you move everything on this path into the CPU to get that shorter wire length.
Okay. Very last question.
All right.
Sorry, is there a question there? Go ahead, please.
James McDonald from Kestrel Kestrel Institute. First, I strongly agree with the problem with covert channels is often you don't even know they exist, side channels. So you can go decades and transmit information without being aware of it. But there's a notion in game theory of random behavior is often the best defense. If there are two equally good ways of doing something, I pick one at random, and that'll often be the best possible defense against an attacker. So I'm wondering if there's some way in the hardware itself to make lots of small random decisions. I mean, usually hardware, you try to make it very deterministic. But if you touch a page occasionally, you stop execution occasionally, you do these little random things, and that's going to create a lot of noise for the attacker.
Right. You're exactly right. You do some random things, it creates noise, it reduces the bandwidth of the channel, but it doesn't reduce it to zero.
It doesn't reduce it to zero.
Right, it does. There's no doubt about it. And randomizing page placement, randomizing counter data or performance measurement data, randomizing how long certain operations take, will reduce the bandwidth at some performance cost, probably, and then it's just a trade-off. But that's a good example of Mark's temporary fix rather than a permanent repair of the problem. And we're going to have to use those until we find better repairs.
You straight up saw that with the first release of these vulnerabilities. The browsers turned off their high-precision timers.
Yep.
And it's purely as a short-term workaround.
Yep.
The long-term workaround cannot look like that, and that's what we have to be talking about.
Mm-hmm. And when we had the initial analysis of this, we looked at the FIPS specs, which actually there are federal standards for the maximum acceptable bit leakage rate, which is not zero, actually. And we looked at it and said, how does this fit in with the standards that we have?
Okay. Let's thank our fantastic panelists again.
Thank you. Thank you.